Hello, and welcome back to Dr. Logic Awkwardly Does Logic. I've got a couple of very interesting equivalences that you can prove in S5 today. Now, this might not seem like the most exciting of topics, but trust me, when you see how we get to use them, you'll be glad that you know them. So, first of all, I want to remind you of a couple of useful things that we had back in System K. Namely, the first one, the distribution of necessity over conjunction. So if P and Q is necessary, then both of the individual conjuncts are necessary. And the equivalence, well, it's an equivalence, it goes both ways. From this, you can also get what is the dual of it, which is that if you've got a possible disjunction, then this means that either one of the disjuncts or the other disjunct is possible. So this is super useful because what it allows you to do is it allows you to take modal operators and shove them inside of parentheses. And this is what we want to do if we are trying to find kind of the most basic, most simple way of representing a modal formula. However, what you'll see is that one of these involves conjunction and necessity, the other involves possibility and disjunction. We don't have anything that mixes the two of them. And in particular, you can easily see that something like maybe P or Q might be necessary, but it's not going to be equivalent then that either P is necessary or Q is necessary. Just consider P or not P. It's a tautology. It's true in all possible worlds. Therefore, it is necessary. But it doesn't follow from this that either P is necessary or not P is necessary. So we don't have anything like this. What we are going to get, though, in S5 is something very much like this, just involving one more modal operator. So I'll give you the first one, and then once we can show that this is a theorem of S5, that we can give a proof of it, three other principles follow from it very, very easily, just through contraposition, substitution, all of our standard usual tricks. So the one that we're going to start with is this. If we have a disjunction where one of the disjuncts is necessary, and this entire disjunction is necessary, then this is going to turn out to be equivalent to essentially distributing the necessity over the disjunction, and then, because two boxes is equivalent to one box in S5, deleting one of the boxes. So what we're going to show is that you can distribute necessity over disjunction and possibility over conjunction when one of the disjuncts or conjuncts already has a modal operator on it. So this is the first theorem of the day, and we can prove it as follows. So we start off with just a simple substitution instance of a theorem of K. So I will write it out and then tell you, what this is a substitution of. So if we have, it's necessary that either P or necessary Q, from this, it follows that either P is necessary or necessary Q is possible. So this is uniform substitution, and all we have done is replaced plain old Q with necessary Q in a theorem of K. So the theorem is just exactly this, but without the boxes in front of the Q's. So if a disjunction is necessary, then either one disjunct is necessary or the other one is possible. And when we have this, we can then substitute in the necessary Q. So now we've got one of our reduction laws, which says if I have a box and a diamond and then a box, I can reduce this to just a box. So this is an S5 reduction law that we saw in one of the previous videos applied to line 1. So this gets us one half of what we want. Now we need to go back the other way. So again, we're going to take another substitution instance of a K theorem. Again, I will write out the substitution instance and then explain what the theorem is in case you don't have all of your theorems of K memorized. But this is that if either P is necessary or Q is necessarily necessary, then it's necessary that either P or necessary Q. So this is uniform substitution on a theorem of K. And again, we have just replaced ordinary Q with necessary Q. So this is the theorem of K, not the same one as the one that we cited in the first one. It's the one that says if either P is necessary or Q is necessary, then, of course, the disjunction between the two of them is going to be necessary. But again, we've got an S5 reduction rule, which says when I've got two boxes, I can reduce it down to just one. So if either P is necessary or Q is necessary, then it's a necessary that either P or necessary Q. So this is another S5 reduction law applied to line 3. And that's it. We've now got, if it's necessary that P or necessary Q, then necessary P or necessary Q, and the converse. So we can put the two of them together. Oops, let's put that box on the outside where it belongs. That necessarily P or necessarily Q is logically equivalent in S5 to necessary P or necessary Q. And this is just propositional logic stitching together 2 and 4. So there you go. That's the first one. We can then very easily get, just through uniform substitution, from this formula, we can, all right, let me erase this proof so that we've got some space to write down the other ones. Most tedious part of doing logic is removing all of the work that you don't want to have anymore. So the second one that we want is just by putting a diamond instead of a box on the Q. So it's going to be the case that it's necessary, either P or possibly Q, if and only if necessary P or possibly Q. So this is going to follow from the previous one, just through an appropriate choice of universal substitution. So I will note this from 1 by universal substitution. Figure out the substitution instance yourself. It's straightforward, but it's still a useful exercise. So what these two together show is that so long as one of your disjuncts has a modal operator on it, either a box or a diamond, you can then essentially distribute the box over the disjunction and reduce what would have been box Q or box diamond Q to just box Q or diamond Q using our standard reduction principles. We can also get essentially the duals of these, so the ones involving possibility over conjunction. So I'll write both of these down and then explain how you would go about proving them. So if it is possible that P and possibly Q, this is going to be equivalent to possibly P and possibly Q. And similarly, if it is possible that P and necessary Q, this will be equivalent to possibly P and necessary Q. So 4 follows from 3 in the same way that 2 followed from 1. And you can get 3 from 1 through uniform substitution, contraposition, and modal interchange. So the idea is if we have, say, necessarily not P or box not Q, if this implies necessarily not P or necessarily not Q, so what you can see is that this line here is just a substitution instance of the first line of the proof of 1, but we've changed all of our atoms for negations. And then take the contrapositive of this so that we have, well, if it's not the case that necessarily not P or necessarily not Q implies not necessarily not P or necessarily not Q. Now we can do a bunch of modal interchange. We can do a bunch of De Morgan's, basic propositional and kind of modal stuff that is going to hold in any system. So this would become not box, not P, and not box, not Q through De Morgan's. This one is going to become possibly not P, or box not Q. And then you can do De Morgan's again, and you can change your not box nots to diamonds, and so on and so forth. We've run out of whiteboard space, but you see how this proof is going to go in order to get from essentially changing all of the boxes for diamonds and all of the ors for ands. This is a common type of proof mechanism that we have seen, not just in S5, but in other ones. These four are essentially the last theorems in our toolkit, because what they allow us to do is, with the S5 reduction laws, it means that we can take any string of modalities, reduce it down to just one, and then with these four laws, we can make sure that every single modality is attached to an atom. It doesn't have to scope over something more complex. So you can see this on the left-hand side. We've got a box that scopes over something that has another modal operator in it. But on the right-hand side, we don't have that. The modal operators only govern atoms, or it doesn't matter if they're atoms. They could just be more complex, but purely propositional formulas. This is going to give us the last bit of the puzzle piece that we need in order to prove something really cool, which is that every formula in S5 is equivalent in S5 to something that only has a single modality attached to something that is non-modalized. This will be a type of normal form theorem, and we will prove it in the next video. So join me then. Until then, take care. Cheers.